Okay, boys, class 12. It is our fourth video number 4. Here you will see the diagrams of tetrahedral void, diagrams of octahedral void, and diagrams of FCC unit cell. Here I want to give you the exact idea of the location of tetrahedral void, location of octahedral void, how is the ratio 1:1:2 coming as we discussed in our theoretical class. Now see, here you see the figure of tetrahedral void, 3 spheres touching each other, and this sphere, it is shown above, but it will be landing on the triangular depression of these 3 spheres. So it is shown separately, but consider this sphere will be landed on these 3 touching spheres. That means all the 4 spheres will be touching each other. Now if you join the center to center of these 4 spheres, you will get a tetrahedron, and that's why the void which is created between the space of these 4 touching spheres is known as tetrahedral void. So actually the tetrahedral void is surrounded by 4 touching spheres. The void is not spherical. The void is not spherical, but here we have shown here with the help of a small sphere that can be exactly fitted in the void. That can be exactly fitted in the void. Radius of that small sphere which can be exactly fitted in the tetrahedral void is called radius of the tetrahedral void. Now if you consider the radius of the sphere is r and radius of the tetrahedral void is rt, geometrically you can derive the relation between the two, and the relations between the 2 radii rt by r, this will be coming 0.225. So radius of the tetrahedral void is to radius of the sphere, or you can say the ratio of the radius of the tetrahedral void to that of the radius of the sphere is equal to 0.225. Now come to octahedral void. Here you see the octahedral void, 4 touching spheres in the same plane. There is a sphere which will be placed from the above, and there is a sphere which will be placed from the below, so that all the 6, 1, 2, 3, 4, 5, 6 spheres will be touching each other. Now these 2 spheres are separately shown so as to understand the figure, but actually this figure is just above these 4 spheres, and this sphere is just below the 4 spheres touching each other. So consider this space. This space is surrounded by 1, 2, 3, 4, 5, 6 spheres, and whose centers, if you join by imaginary lines, the centers, if you join the center to center of these 6 spheres, you will get a regular octahedron. That's why the void is called octahedral void. So octahedral void, if you want to see the octahedral void, it is shown spherical, but it is not exactly spherical. It is we use this term, that radius of the octahedral void, we use this term. So radius, whenever radius is coming, you might be thinking that the void is spherical. Void is not exactly spherical. Then what is the concept? The concept is a small sphere which can be exactly put, which can be exactly fitted in this space, which is enclosed by 6 touching sphere. The radius of that sphere is known as radius of the octahedral void. So listen to me once again. The very small sphere that can be exactly put in this space which is surrounded by 1, 2, 3, 4, 5, 6 touching sphere is called radius of the octahedral void. So if you denote the radius of the octahedral void is RO, and radius of the sphere forming the octahedral void is R, capital R, then the ratio is equal to 0.414. So radius of the octahedral void to that of the radius of the sphere, this is equal to 0.414. From these two relations, one thing is clear, that radius of the octahedral void is always greater than radius of the tetrahedral void forming by same sphere. So when the particles, same particles forming tetrahedral void in one lattice and same particles forming tetrahedral void in the same lattice in other locations, then this can be said that radius of the octahedral void is always greater than radius of the tetrahedral void. From this, you can see radius of the octahedral void is 0.414 times of the radius of the sphere forming the octahedral void, and radius of the tetrahedral void is only 0.225 times of the radius of the sphere forming the tetrahedral void. So this can be written that Rho is greater than RT for same lattice in which tetrahedral voids and octahedral voids are forming. Now, after this, I want to discuss you the location of tetrahedral void and octahedral void in a CCP lattice. So CCP lattice means this is a face-centered unit cell. The octahedral voids, where the octahedral voids are exactly lying, you can understand it. See, tetrahedral void is lying. First I am telling about tetrahedral void. Tetrahedral voids are located just inside the corner of each particle. Here is a corner particle. These and these are touching, face centered. These three particles are touching each other inside, and there is a particle at the top. So just below this corner, there is a tetrahedral void. So here is a tetrahedral void, here is a tetrahedral void. How can you explain it? Same concept, three spheres just surrounding three face-centered spheres. Every corner has three face-centered spheres. Suppose if you consider this corner, here is a face-centered particle, here is a face-centered particle, here is a face-centered particle. So just look at this edge. Here is a particle, corner particle, here is a face-centered particle, here is a face-centered particle, here is a face-centered particle. These three face-centered particle, 1, 2, 3, three face-centered particle, and just above it there is a particle at the corner. So this particle and along with these three face-centered particle will form a tetrahedral void. So tetrahedral void is located just below each corner, सभी कॉर्नर के जस्ट नीचे. जैसे ये कॉर्नर मानोगे तो ये फेस सेंटर्ड पार्टिकल, ये फेस सेंटर्ड पार्टिकल और ये फेस सेंटर्ड पार्टिकल, ये तीन फेस सेंटर्ड पार्टिकल जो हमने थ्री फिंगर से दिखा रहा हूँ, ये थ्री फेस सेंटर्ड पार्टिकल एंड देयर इज ए पार्टिकल जस्ट बिलो द कॉर्नर. सो आई मस्ट राइट हियर दैट tetrahedral voids are located just below each corner. Just below each corner. Tetrahedral voids are located just below each corner. So there are how many corners? 12 corners. There are total number of 12 corners. 12 corners. So 12 tetrahedral voids. Okay. Just below each corner. Sorry, 1, 2, 3, 4, 5, 6, 7, 8 corners. I am wrong. 8 corners. So 8 tetrahedral voids. Now it is clear. Just below each corner. There are 8 corners in FCC lattice, CCP lattice, and same is found in case of hexagonal lattice. But hexagonal lattice, the locations are slightly different. I am telling you about CCP and FCC lattice. So there are 8 corners, means there are 8 tetrahedral voids per unit cell. Per unit cell. Now come to octahedral voids. Octahedral voids, it's somewhat difficult to understand that octahedral void is created at the center of each edge. Here is a edge, here is a edge, here is a edge, here is a edge. So how many edges are there in a cube? There are 4 plus 4 plus 4, 12 edges. So at the center of each edge, here is a center of the edge, here is the octahedral void formed. At this point, octahedral void will fall. How it is octahedral void? Just try to understand that another unit cell is there, another unit cell is above it, another unit cell is above it. So remember, so the octahedral void is formed at the center of each edge, and you know that each edge is shared by 4 unit cell. Each edge is shared by 4 unit cell. Edge shared by 4 unit cells. 4 unit cells. Remember it. Every edge, when packing is observed, if you look at the entire packing, then every edge is shared by 4 unit cell. This is 1 unit cell, this is 2nd unit cell, this is 3rd unit cell above it, 4th unit cell above it. So every edge is shared by 4 unit cell, and there is a octahedral void formed at the center of the edges. Now the particle 1, 2, 3, 4 particles. See, 1, 2, 3. Here is a face center particle. Here is a face center particle. 4 particles. 1 above, face center particle above. 1 face center particle below. So 6 particles. See, 6 particles. 2 here. This is a unit cell. 2 here. 2 here. Corner particles. 2 here. Face centered particles. Clear. 2 here. Face center particle. 1 is this unit cell, another belongs to the next unit cell. So 6 particles surrounding this center. 6 particles surrounding this center. See, remember, 1, 1, 2, 3, and next unit cell 4, 5, and the above unit cell 6. 6 particles surrounding every edge of this CCP lattice, CCP unit cell. Now, therefore, this octahedral void is formed here at the center of the edge. That octahedral void is actually shared by 4 unit cell. Now, when you calculate, octahedral voids are located at the center of each edge and there is a octahedral void which is fully belongs to this unit cell. Where is it? It is at the center of the unit cell. How it is center of the unit cell? You know that if this unit cell has 6 faces, 1, 2, 3, 4, 5 and 6, and every face has a face centered particle. So see, every face has a face center particle, 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 face center particle. These 6 face center particles, 1, 2, 3, 4, 5, 6 will be touching each other inside the unit cell. So 1, 2, 3, 4, 5, 6, 6 face centered particle will be touching each other inside the unit cell. And that's why octahedral void will be created at the center of the unit cell, just center, body center of the unit cell. That octahedral void is fully belonged to the unit cell. Therefore, plus 1 octahedral void at the body centered. So see the calculation. So octahedral voids are located at the center of each edge, plus there is an octahedral void which is lying at the center of the body of the unit cell. Therefore, if you do the calculation, the number of octahedral voids equals to at the center of each edge, number of edges equals to 12. Number of edges of FCC unit cell is 12, clear, and each octahedral void is shared by 4 unit cell. Therefore, the part of the octahedral void that will be belonging to a particular unit cell equals to multiplied by 1 by 4. A octahedral void 4 यूनिट सेल से शेयर्ड है, तो एक एक यूनिट सेल में इसका कंट्रीब्यूशन कितना जा रहा है 1/4. तो कंट्रीब्यूशन टू ईच यूनिट सेल is 1/4 only, plus there is a octahedral void which is at the center. So 12 into 1/4 plus 1, this is equal to 4. Now see, number of octahedral voids equals to 4 and number of tetrahedral voids equals to 8. See, this is the number of tetrahedral voids. In a FCC lattice, where they are located? A very simple thing. Tetrahedral voids are locating just below the corner of each particle, just below the corner particle you can say. So there are total 8 corners, so there are total 8 tetrahedral voids. And octahedral voids, every octahedral void is located at the center of each edges, but its contribution to the unit cell is only 1/4. There are 12 edges, 12 into 1/4, that is equal to 3 octahedral voids, and there is an octahedral void at the center of the body of the unit cell that is fully belong to this unit cell. And so it is 12 into 1/4 plus 1, that is equal to 4. Now see, you look at this relation. The number of spheres is to number of octahedral void is to number of tetrahedral void. You want to get this ratio, number of sphere, number of octahedral void, number of tetrahedral void. See it here clearly. The number of sphere in FCC unit cell, you know that there are 4 spheres. So number of spheres equals to 4. Number of octahedral voids equals to 4. And number of tetrahedral voids equals to 8. So once again I am telling, number of spheres forming the unit cell, because we have done the calculation per unit cell. So number of spheres equals to 4. Total number of spheres present in the unit cell, in FCC unit cell is 4. Number of octahedral voids 4, as calculated, already calculated. Number of tetrahedral voids 8. Therefore the ratio is 1:2. This is the ratio. In this way it is coming. Now it is clear that in FCC lattice or CCP lattice, the unit cells are FCC, whatever be it, CCP lattice or FCC lattice बोलो, unit cell FCC. And FCC lattice में कहाँ octahedral void located है, कहाँ tetrahedral void located है, इसका जानकारी आप लोग को मिला है और ये जानना भी चाहिए. तो इससे हम लोग को पता चला जो कैसे हम लोग कैलकुलेशन कर रहे हैं, ये कैलकुलेशन हमने आप लोग के सामने दिखाए. Now the next point is the same ratio, but the calculations are different. So the same ratio is found to be existing in hexagonal lattice. Hexagonal lattice forms hexagonal unit cell, and the same ratio is maintained there, 1:2. But the calculations and locations of the tetrahedral voids and octahedral voids in hexagonal unit cells are different. That if you want to know it, you can take the help of your reference book. That is not in your syllabus here, board syllabus. You can take the help. That where exactly the tetrahedral voids and octahedral voids are locating in the hexagonal unit cell. But ultimately when you calculate, the same ratio will be coming. Not only this, the packing efficiency of HCP and packing efficiency of CCP, they are also same, 74%. These are the similarities which we have already discussed in our previous class. Now you see density that we have discussed it. Density of the solid. Density of the solid equals to density of the unit cell. Remember it. Density of the solid equals to density of the unit cell. Density of the solid equals to density of the unit cell. So because you know that density is an intrinsic property, it does not depend upon the amount of mass. That's why from a very small block of the solid, that is unit cell, if you find the density will be same for the solid also. Now density of the unit cell, D equals to mass of the unit cell mass of the unit cell by volume of the unit cell. Volume of the unit cell. It's a very important thing that you are all knowing. Now you know that different unit cell have different number of particles. So this number of particles, for this we are writing a factor Z. Z into mass of each particle, mass of each particle, Z into mass of each particle by volume of the unit cell. Volume of the unit cell is A cube. Now mass of each particle depends upon its molar mass. If the molar mass of the solid, molar mass is taken m, then mass of each particle will be m by Avogadro's number. Molar mass is the mass of the Avogadro's number of particles. Therefore, mass of each particle will be m by Na by volume of the unit cell A cube. Therefore, finally we are getting D equals to Z into m by A cube into Na. Here you remember that you are finding density, so better if you find the density in kg per meter cube, or you can find out the density in gram per centimeter cube. These way. So if the age is given in picometer, you will convert it to centimeter. You can directly put the molar mass, whatever it is given, that will be in gram. So you will get it gram per centimeter cube, remember. But if the molar mass is given, generally molar mass is given in gram per mole. Say for sodium, molar mass is 23 given, gram per mole. So if you want to find out the density in kilogram per meter cube, then you have to convert the molar mass into kilogram, and volume of the unit cell, it is given in picometer, you will convert it in meter. Volume of the unit cell, you will convert it in meter. Then you will get in kg per meter cube. So remember, two things are there. Molar mass is always given in gram per mole. Okay, molar mass is always given in gram per mole. So the A is always given in picometer or nanometer, something like this. So whatever you have to do, you have to convert the unit of length A's length in meter, and you have to convert molar mass in kilogram by dividing by 1000. Then you will get it in kg per meter cube. And another way, that is the shortcut way, that molar mass is already given in gram. So convert A in centimeter, convert A in centimeter. Now you will get the unit of density in gram per centimeter cube. Sometimes what is given, as already discussed in our previous class, the number of particles given, occupying tetrahedral voids, octahedral voids given. I think you have all these things you have understood in the previous class. Okay, boys, thank you. We will next meet you in the next video. That is the last part of the chapter. Thank you.